All right, guys, let's go over quickly what we need to do for paper 2, especially with the use of a calculator. So this video will quickly demonstrate what we need to know about the use of a calculator for AA students. For AI, I demonstrate a lot of use of a calculator in the last minute revision video, so please check it out for the AI students. This is specifically for the AA students, okay? So without further ado, let's get started. So yeah, I gathered some questions on the from each topic that would probably require a certain use of a calculator. So without further ado, let's get started. So yes, the first one here says, for the sequence and series, yeah, you're right. For the solver. So let's have a look at this question number 1. So it is something with the repayment, and I don't think you have to be familiar with the financial solver on your calculator for AA students. And also, furthermore, I think what you will be asked to do is to demonstrate the equations. Okay. You need to show them how you have derived those equations in an expression. So for this one, I wouldn't go over this with the repayment on the financial solver. We're trying to derive the recursive relation. So let's talk about what I mean by that. So this is from the last exam question. This is from the exam question on the sequence and series, especially for the repayment. It says, as soon as Mary was 18, she decided to invest 15,000 of this money in an account of the same type, earning 0.4% interest per month. So let's say that this was going by, compound interest. So let's say that this was a compound interest, okay? Because the previous section of the question was talking about the compound interest. And she says that she withdraws $1,000 every year on her birthday to buy herself a present. So determine how long it would take until there's no money in the account. Okay, so this is a great question. For the repayment, what I want you to remember is that yes, the balance is going up, right? So either your debt or your investment will go up, but you deduct some money, right, to pay the bill, or in this case, to buy yourself a present. So you are using what you have in your stack, and so for that, the formula is going to be the geometric sequence minus, right, the repayment times the geometric series. Okay, and then you want that to be equal to 0 because you want to be able to fully pay back, right? And how you have derived that formula is the following. Well, I do explain this in the AA revision video. I want you to check it out. The essence of this video is to demonstrate the use of a calculator, all right? So if I quickly, use that formula, and then, get into the use of calculator. So for our geometric sequence, I want you to realize that it's going to be 15,000, right? And then the common ratio, in this case, you're right. This is a monthly interest. So this would have been 1.004, right? For the common ratio, for the monthly, right? However, you're absolutely right. I am changing to yearly because I cannot split my birthday present into 12 different division, right? So we got to make the interest rate into yearly so that you are in the same time interval. This is very important. So I'm going to put it as a 12 and there, you see? And then, so maybe I will let that 1.004 to the power of 12 as my common ratio R. Okay, so if I use that common ratio, my balance is going to go up by the geometric sequence. However, I am spending every $1,000 every year, so that's great. And then with this common ratio, I'm going to create a geometric series, which is r to the power of n minus 1 over r minus 1. And I want to let that to be 0. And as you can see, yes, there will be a lot of chance that I have to use this 1.004 to the power of 12 in my calculator. And if you ask me how to solve for the n, I will use NSolver because this is exponential. It's very likely that it's going to be 1-to-1. So yes, the logic of using the NSolver is that I know that this is a 1-to-1 function. So let's try to use it. So if you want to use NSolver, so you always should memorize the keypad on the NSpire. It's menu 3-1. I don't want you to scroll down. I don't want you to look at the menu and wonder where my NSolver is by now. You need to be able to press menu 3-1, or simply just type NSolve on your keypad on the calculator. That is also fine. So if I do NSolve, as you can see, it's in italic. That means it's not in program yet. So, but if I complete writing the program correctly, then it becomes non-italic. That means it's programmed now, right? So you can start using it. But it's very tedious. It's very tedious, isn't it? To put 15,000 times 1.004 to the power of 12 times x all the time. I don't want that. So what I also want you to realize is to store. It's a store command, right? So I know my common ratio, my friend, is going to be 1.004, which was a monthly rate, right? Sorry, was it 0.04 or yes, 0.4? So 0.004 is great, but I had to make it yearly. So I'm going to put it as to the power of 12, isn't it? And then I'm going to store that. So for the store here, you can then choose any alphabet you want. So let's call it R, right? To indicate that it's going to be the common ratio. So, and then, if I just put random numbers and put the R again, it's going to be representing the number that I stored. That's great. So that I don't have to hassle, you see, to put that 1.004 to the power of 12 in my equation, because for my repayment, it's going to appear quite several times. So instead of writing all that, now I can do NSolve. And what was it? It was a 15,000, which was my balance, increased by the r to the power of n, which I don't know the, I'm looking for the number of periods. So I'll put that as an x, no problem. Minus $1,000 for the birthday present every year. And because if it's a repayment, you should do, what is it? You should do the geometric series for the repayment. However, here's the thing. Yes, it was r to the power of n minus 1 over r minus 1, right? It involves a division. So what you can do, sure, is put the bracket, put the expression, and then divide it by, right? However, I prefer putting in quotient form so that you try to minimize the mistake, because if you use the bracket and division method to represent a fraction, you are vulnerable to make mistakes sometimes. But if you put it in quotient form, it's very unlikely. And if you ask me where that quotient is, you simply have to put the command, okay? Sorry, so let me just quickly type nspire. Yes, you just have to press the, Control and division. That will create the quotient right away. Right, that's great. And by the way, the store on the calculator is on top of the var. So if you press Control, var, it can get you STO, and that is great. So please, if you want to demonstrate the fraction, press Control division to create the quotient. So now I have it. I'm gonna do then r to the power of x minus 1 over r minus 1 is equal to 0, and I'm looking for the x. Then it can beautifully find me the equations. But I want you to know how concise this is, because I don't have to put the r as a 1.004 to the power of 12 every single time, because I stored it, okay? So make sure you understand about the store. All right, let's move into the next question. So if you quickly go to the next question here, so it's finding the nth term. You're absolutely right. We want to put it into the geometric sequence, right? So if you have a look, so it's going to be, negative 1 over 2 to the power of, n minus 1 for the general formula. And then I want to find the 11th term, right? But you know what? Let me just quickly change this, okay? I want to find the nth term that it becomes, let's say, less than 0.0001. What if I wanted to solve that? So less than 0.0001 is what I'm looking for, you see. However, yes, you're right. But this is a little bit more confusing because this is an alternating, right? This is an alternating sequence. And if you use NSolver, you might have some problem if you were to put that negative base. But you know what? Let's do it. So yes, the reason that you should put the NSolve in the calculator is when you are convinced that you have a one-to-one relation, right? So if you have, for example, quadratic expression, let's say you are looking for NSolve and x squared equal to minus 1, and then you know that the solution is quite trivial. You know it's positive or negative 1, right? But if you ask the calculator to solve it, even though that we know there are two solutions, it's going to only give you one least positive solution. And I don't like that because it does not give me every solution. So unless you're dealing with the one-to-one functions such as an exponential, logarithms, linear, I really do not suggest to use it. If you got a quadratic polynomial or trigonometric function, please do not use NSolve, but instead please use the graph, okay? But if you ask me how would I use the NSolver to find the negative solution, in this case -1, well, you can restrict your bound. So you can do the lower bound, upper bound like that. So for example, if I restrict my domain from -2 to -0.5, it will get me -1, as you can see. However, this will then suggest that you already know your solution is around where, but usually we don't know it because we need to use our calculator to find the solution. So again, if to quickly demonstrate, to quickly point out, if it's not one-to-one function, do not use NSolve. But our question was somewhat different. So we do know that it was one-to-one, which was a -1 over the exponent form for the geometry. However, it simply was having the negative base. But you know what? Let's ask calculator. Let's ask a calculator. So it's going to be -1 over 2, right, to the power of n. X is equal to 0.001. Okay, so why not, right? So let's do that. I'm looking for the x. As you can see, no solution found because it's alternating, and maybe we don't have exact value of x that would become the 0.01 when we was having negative, right? So that for that problem, what I would do is slightly change the value. So I'm gonna go with the positive. Then it gets me the value, right? Then it gets me the value. So what you can do is to put that number around your sequence and see if it became, less than 0.01. So if I put now -1 over 2 to the power of 9, as you can see, it's a negative number. It's obviously less, right? But if I put 10, that's also, if I demonstrate approximate, it's also less, right? Oh, well, yeah, you're actually right. All of them is going to be negative because what is it? It's negative value, right? But yeah, so what I wanted to demonstrate here is for the if you're looking for the exact solution with the negative base, which is going to be very rare for the question to ask because they don't like working with the negative base, the NSolver may not work. Okay, so you need to make sure then to try without the negative base and then play around with the number around it. Okay, is my point. Yeah, but I think the question would have been better for the largest possible n, so that it's going to be bigger than 0.0001. Okay, but so be it. So the point I'm trying to make here is for the NSolve, one-to-one only, and for the negative base, try to lose the negative base and then play around with the number around it, is what I'm saying. Okay. And yes, so little commands to memorize. So for the sequence, if you want to generate the terms, right? So if I quickly go to the calculator, so for example, so if I go to graph here, right, and then you can press the graph entry, and then you can go to the sequence, and then here you can put two things. You can put either explicit form or recursive form, right? So if you remember, my friend, that the recursive definition for the arithmetic sequence is that my present term depends on the previous term. So you're going to say u4 of n-1, that's your previous term, plus the constant value such as a 2 is going to give you the arithmetic sequence with the common difference of a 2. But for the recursive form, my friend, you need the initial term such as 1. If I put 1, then it's going to demonstrate a sequence starting with 1 with the common difference 2. So as you can see, my first term was 1. My second term is going to be 3 because you add it by 2. You see? So on the calculator, it is possible to demonstrate not only the recursive, but also the explicit. So for the explicit, what I'm going to do is just put 2n minus 1, right? And for that, you don't need the explicit form because you already gave the explicit. So if the calculator put n equal to 1, it's going to have initial term already. So if I do that, you get the same thing, right? So be able to generate those sequences using the graph entry on the sequence, okay? But also you should be able to generate the terms with the given that equation. So what I mean by that is the following. Check this out. So if I let, for example, my friend 2x minus 1, right? And then what you can do is to use something called a given that. Where is it? I believe it's here. Oh yeah, there you go. Given that. And then you know what? I'm going to put x equal to 1, 2, 3. So as you can see, it's going to put the values for the x equal to 1, 2, 3 into the expression. So you can use this given that formula to find the several value okay, as you wish, right? So for example, if I was doing, you know, sine x, and I want to see what value I'm gonna get if I put x equal to, let's say, you know, pi over 6 and pi over 4. Let's have a look. So given that let's say x is equal to the bracket, the domain. So let's say I'm doing pi over 6 and pi over 2 and negative pi over 6. So you know it's going to be half 1 and negative half. And then let's see if I get that, and I do get it, right? So you are able to generate with the given that. So please make sure you try to use it if possible. Okay, and if you ask me where the given that is, on the NSolver calculator, it's right there. So if you press what is a control equal, and the first part here it says given that, then that's where you can give a condition. It's a conditional statement for the use of a calculator. So that is great. Okay. But I never really had it. It wasn't really useful. But it gets useful when you graph it, because you can restrict your domain. But anyways, let's have a look at this recurrence relation. So it's a very, very nice example to demonstrate on the graph. Okay, so the reason I wanted to talk about here was that I think this recurrence relation can be definitely a potential question for the paper 3, but you can demonstrate the sequence behavior by using the recurrence relation. It says my present term is equal to 1 over 1 plus the previous term, and for the recursive definition you need to have your initial condition, and it's such as 1. So that is lovely. So what I'm going to do is go to the graph here, graph entry, and then I'm going to put, what is it, sequence, and sequence here. Now I'm going to put a recursive definition. So fraction, right? Always remember, if you want to represent the fraction, please try to use the quotient. Do not try to use the division, because you can make some mistake if you missed one of the bracket there. But anyways, it was a 1 over, what was it? 1 plus previous term, so 1 plus 6 of n minus 1. But for that recursive definition, I need my initial term. So I'm going to put that as a 1. So I see the behavior, as you can see. It looks like it's decreasing. So what I'm going to do is maybe I will do the zoom fit, right? To ask calculator to demonstrate is more in a more fitting way, right? So that I'm going to go menu 4.1 and then press A. Sorry, menu 4. And then menu 4A. So it's going to make a zoom fit. So as you can see, it seems like it's converging, you see? It seems like it's converging, my friend, right? And that convergence, you can sort of see the behavior if you go to the menu. Okay. It's got table. It says split screen table. I'm going to click that. So then if you scroll down, as you can see, as the term gets bigger, then I have a convergence. So I'm going to say my sequence converges to 0.618 is what you can do. Okay. So it's a very nice a way of finding the limit of a sequence. Okay, so make sure you are able to visualize on the sequence if you have to. And I think maybe this is going to be useful for paper 3, not so much for paper 2. But anyways, let's have a look. So let's have a look at the question number 9. Oh yes, you know what? This is a really, really super duper important question. This is a super duper important question because it's all about your confidence. You know what? As I've told you before, my job here is not to solve the problem, but demonstrate the skills. Demonstrate the skills you need, all right, for working with the calculator. So yes, you know, I will attach this document obviously on YouTube, and make sure you try to solve on your own. Try to create the equation what I'm about to tell you. Okay, but you know what? I will give you the formula right on the video because I want to get into the business of working with the business of use of calculator. So here's the thing. So the inequality that you're trying to use for last question, this is very, very important. Very, very important. Okay, very important. Is that you're trying to see when the investment method by Freya, which is going to be given as a 10 times 1.01 to the power of n minus 1 over 1.01 minus 1, and then the Carolina is a Cn is going to be given by n over 2 and 2n plus 18. So this is done by the arithmetic series. How do I know it is arithmetic series? Because this is a quadratic expression, and a sequence with the quadratic expression without the constant term is already telling us that it's working with what the arithmetic series. So, you know, we should know that right away. And then this is exponential form. So this is a geometric series. And for the financial sequence series related problem, it's going to be considered superannuation. You are adding and the fixed amount of money on top of the compounding is what it means by the superannuation. But at the moment, I want to just focus on the calculator use, okay? And I'm looking for the time. When this Fn gets bigger than the Cn. That's the moment I'm trying to find, okay? And this is super important. I really want you to fasten your seatbelt. Because when you're solving inequality, it is not just about the sequence. It's generally for the function as well. Think about this, my friend. And this is exponential. This is a quadratic. So as an AA student who is very good at analysis, is that you know already, my friend, the exponential function is going to be eventually bigger. You must know that. So you do not get that answer from you do not get that understanding from the calculator. You have that from the understanding of a function. This is super important. And therefore, you're able to roughly graph the picture. The graph, I'm sure it's going to look like exponential and then quadratic like that, right? Look at this. It's going to be quadratic. However, I know eventually, my friend, that the exponential is going to get bigger than the quadratic. Not so good at the drawing, sorry. We know eventually the exponential is gonna catch up. We know that, right? So even though you put the graph on the calculator, it seems like the quadratic is always bigger, then you should question yourself, hold on a sec, that's a wrong picture, because I know exponential must get eventually be bigger. Why is it suggesting that the quadratic seems to be the largest in that interval? Because we didn't set up the interval correctly, is what I mean. So this is going to be a very, very sort of a mistake eliciting problem, right? So make sure you do not fall for that. So let's have a look. Let's try to put that expression on our graph and compare the function between, right? So what the first function that I'm going to put is what? It's going to be 10 times the investment method by Freya, 1.01 to the power of x minus 1, sorry. And then 1.01 minus 1 is the geometric progression. That was a geometric series. So I got that exponential function. And I'm going to put another one with the quadratic, which was the arithmetic series. So x over 2 times 2x plus 18 is what I've got. So that's the arithmetic series. And as you can see, it's not very good scale. So what I like to do, my friend, is that I'm going to do menu 4-1. Let's do menu 4-1. Always, if you want to change the setting, please press menu 4-1. So I'm going to do the menu 4-1 like that. And then let's put 0, then let's go by 20. Why not? And then I'm going to ask my calculator to make it more fitting by press menu 4A by the zoom fit. But look at this, my friend. Look at this. The blue represents the exponential. Red represents the quadratic. And it seems like what? The quadratic is always bigger. Then you're inclined to make a judgment, make a decision that, oh, okay, you know what, the Caroline progression from the quadratic seems to be always bigger. So I would say the inequality can never be true. But we know that's not true because we know exponential will eventually catch up. So I just have to increase. The amount, the input, right? It was from 0 to 10, 0 to 20. Maybe I need to increase up to 50. Maybe I need to increase to 100. Who knows? But I know with the full confidence that eventually the exponential is gonna be bigger. So you shouldn't give up, right? So that's what I'm saying. So let's have a look. Why not? Let's go menu for 1, and then let's go with going maybe up to 100, right? 100. Let's go 100. I got that, but it looks like what? That if I do the zoom fit again, yes, the quadratic is very big. Because if you think about the base is almost 1. My base of exponential is almost 1. It's a 1.01. So it takes a lot of time for this to be actually exponentially fast, right? So you actually have to have a significantly bigger input than usual, because if 100 gave this much, I'm sure it's gonna take a lot more time for us to demonstrate for a bigger impact on the exponential. So you know what, let's be bold, let's go for 700. Why not? So I'm going, because I know I need to explore that on my own, because I understand the exponential function must be eventually bigger. So I will go for 700. Why not? And then let me make a zoom fit. Oh, hold on a sec. Now you see that this exponential finally caught up, right? The quadratic and eventually got bigger exponentially. So that full confidence is not given by the calculator. It's not given by ChatGPT, but it's given by your logic that you understand that exponential is going to be eventually be bigger. So yes, the use of calculator does not give you the answer right away. We have to think. We know the geometric sequence, which is an exponential, is going to be eventually much bigger than the arithmetic series because it's a battle between the exponential and quadratic. So yes, if I try to find the intersection right there, analyze graph, intersection, choose a lower bound and upper bound, it's 590. It's a 590, my friend. Okay. So that's the moment you know, okay, so after 590 months that the Freya is going to earn more, her investment is going to make more money than the Caroline is what they're saying. Okay, so that confidence is important. It's not from how well you use your calculator, but how you understand the progression function. Okay, good. So you know the examples are given there, so please have a look. Let's continue to the next section for the possible use of a complex number with the calculator. But let me take a 5 and come back to you. All right, let's have a look at the next question with this possible use of a calculator for the complex number, right? So imagine that you were given a quadratic as the following. So, polynomial as the following. Let's say it was a x plus 4, x minus 2, x squared plus 3x plus 4, right? So suppose that that's my polynomial. Then, you know, the solution here suggests it's going to be -4, 2, or -3 plus minus square root of 9 minus 16 over 2. So that's going to be -3 plus minus square root of 7i over 2. And I want to put that into the, what is it? The Euler form. So then, you know, you got to find the argument. So modulus is 4. Argument will be simply pi. For 2 will be simply just the argument being 0. So that's okay. And however, for this one, you're right. I need to find the right modulus and the right argument. So for the modulus, it's going to be square root of 9 over 4, 7 over 4, isn't it? So that's 16 over 4. That's 2. So for that one, it's going to be 2 cis. Sorry, Euler form, right? And I got to find the argument. So imagine that I wanted to find the argument with the positive in between first, okay? And then yes, you know, for the complex number, if you want to find the argument, we use the typically the tangent, right? So if I call the argument of z as a theta, then tangent theta is going to be the imaginary part of the real part, right? Okay, I got that. So it's a -√7 over 3. That is a great. And now I wanted to find the theta, then I can put the theta is equal to inverse tangent of -√7 over 3, which we can easily put that on the calculator. If you did, I got the theta to be -0.723. And would that, my friend, be a correct answer? Would this be correct? Very good. It is incorrect, right? We got to be very careful. You need to always understand about the function first, about always the domain first, before you actually use in the calculator. Because if you remember, my friend, the arctangent is a very interesting function because it has a two horizontal asymptote, -pi/2, and then the positive pi/2. So it goes like this, right? It goes like that. So that is a great. And then what you realize is that it's always bounded by, what is it? The positive acute or negative acute. So if you had put the negative input there, the output would have been the negative acute. That would have been the angle in the fourth quadrant, my friend. That would have been in the fourth quadrant. But of course, if you actually try to visualize this on the Argand diagram of line complex number, the real part was a negative, the imaginary part was a positive. It's in the second quadrant, my friend. And it's supposed to give you the obtuse angle. Okay, it's supposed to give you the obtuse angle. But if you put the arctangent negative, it gives you a negative acute. I don't like it. Okay, so what you need to describe here is that it's going to be you need to use the reference angle. So get the arctangent of a positive √7 over 3, which is going to be 0.723, and then rotate around by pi. So I'm going to go pi minus 0.723. So it's not entirely use of a calculator, is it? Because you have to think, you have to give the fact that it's going to be in the second quadrant. Hence, the inverse tangent wouldn't give me the angle. I need to rotate is what you need to understand. But you're right, actually you could have just used on the calculator and then put it into the polar form, right? So if I, for example, put it as a negative, what was it, 1 over 2 plus 3 over 2 I, obviously it's not the same complex number, but, I'm just letting you know that this is going to be also in the second quadrant, right? So as you can see, the argument will be in the, in the second quadrant, not in the negative acute, is how you can also get it. So use of a calculator can give you that if you put it into the document setting in the polar form. But, this overall, emphasize that when you're solving the trigonometric equation, you need to respect the domain. Where does my negative happen? Because tangent can be negative in the second and fourth, but if you use inverse tangent right away, it is going to only give you one solution because it's supposed to be one-to-one function. Okay? That's great. Oh, wow. I want you to be very, very keen on the topic 2 calculator use, because this really checks your function understanding. So when I'm encountering a graph like this, my instinct tells me that you have to get the domain first. It's all about the domain and range on the function, especially the domain on your own. So here, yes, the 1 minus x squared has to be bigger than or equal to 0. So for that, it's concave down quadratic. I got the -1, I got the +1 there. That's great. So I want things to be bigger than or equal to 0. So it needs to be above the x-axis. So it's going to be x is between -1 and less than 1. So that is great, okay? All right, so when you see this, my friend, then I will use it for graphing. So if I quickly go to the graph here, right? So then let's say that I would put the x times, square root of 1 minus x squared, right? As you can see, even though it does give me the graph, it's not so fitting, it doesn't look so suitable for me to analyze. So what I want you to do is always check on your domain. I'll go to menu 4.1, window setting, right? And in here, you define your domain. You saw that it was between -1 and 1. And for that, I would put, for example, -1.2 and 1.2, because I don't want it to be cut off at the exact moment. So maybe slightly making it bigger will make it even better. So if I do that, yes, it demonstrates my given domain perfectly. However, the y value is not so fitting, all right? For that, you don't have to worry, because now we can ask the calculator. So changing the domain, you got to press menu 4.1. But if you change the range, if you want to make the y value fitting, you can press menu 4a. You can press menu 4a. So I'm going to do menu 4a to make the graph more fitting for me. So I'm very happy with that. Okay, then you can analyze. So make sure, do not just put the function on the calculator, respect the domain, and then respect the range. Okay, so for example, this comes very handy. Look at this. This comes very handy, my friend. Imagine that I have to sketch that function with the 1 over 100 in the front as a coefficient. So imagine that I was doing 1 over 100 times x times, square root of 1 minus x squared, So if I have that, look at this. It looks like a straight line. Obviously, then then I could panic during the exam, because if I see a straight line, maybe I would use that. Maybe, maybe I would panic looking for the other types of functions, but do you realize, first of all, we didn't respect the domain. We know the domain didn't change. It would have been from -1 to 1. So I'm going to put -1.2 and then the 1.2. And then you make the zoom fitting. But look at the y, look at the scale on the y, my friend. It says from plus minus 0.006. That would have been very difficult to come up on our own to demonstrate the function in that bounds. But you don't have to worry, because the calculator does it for you. However, to do that well, you must set up the domain. That's your job. Even if it's a paper 2, finding the domain is your job, not the calculator's job. Okay, so that's very important. So make sure that you always respect the domain. If you restrict the domain, and then you can easily find the range well. However, yes, you got to be very careful with the zoom fit, because let's have a look at this cubic function, my friend. Let's have a look at this cubic function. So I'm going to go with the graph here. So it's going to be, let's say, x cubic minus 2x plus 1. That's my cubic function. So that's a well-known sort of a shape, right? Going up and down and up. However, imagine that, oh yeah, I wanted to make the graph more fitting, so I'm going to do the zoom fit. But if you did, my friend, if you do the zoom fit on the cubic polynomial, it's going to negate that little perk there. So what they are considering is it's a little bit of an aberration. So, but they're trying to make it smooth by sort of ignoring that part by scaling up very large, because your domain here was now put in as from positive to -10 to +10. So they're gonna put those values and then make that range fitting in that domain. So as you can see, it's not so suitable. So if I got a polynomial, I would actually avoid. If I got an exponential function or polynomial where we know the range is going to be quickly divergent, I would try to avoid using it unless you restrict your domain. For example, if we go back to the function, look at this. This up and down, this maximum, local maximum, minimum happens around, where is it? Plus minus 2. So if I restrict my domain, let's say plus minus 2, right? Go Windows setting, if I go to plus minus 2 on the x minimum, x maximum, and then try to demonstrate the zoom fit, I'm sure it's going to look much better than the previous part, because the previous part, the domain was from -10 to 10. The range according to that will probably not demonstrate the local maximum minimum well around the -1, plus minus 1. So it really depends on how you set up your domain. But overall speaking, generally speaking, I would encourage you not to use the zoom fit for the polynomial or exponential where you know it's going to diverge very quickly. Okay? And yes, number 10 is a super important. I already mentioned it. I mentioned it before when we were talking about the the arithmetic series and the geometric series. Here we know this quadratic, right? This quadratic expression is going to be eventually slower than the exponential. However, if you look at this exponential, even though the base is very large, the exponent has a 0.3, so it makes things very small. However, it would be still bigger than 1, hence giving you the eventual exponential growth, catching up with the quadratic and getting faster and faster exponentially. Okay? So we got to have the confidence that yes, I will be able to finally catch up. So even though my quadratic seems a lot bigger previously, eventually it is going to get bigger. So I would expect to have obviously depending on how many intersections, but at most I would expect 3 intersections. Okay, so if you only see 1 or 2 intersections, you got to question yourself. You need to see if the graph demonstrates that eventually the exponential function is gonna be bigger. Okay, so let's check this out. So I'm gonna put a graph on it here, and then let's try to compare. So I got the x squared minus 3x plus 1. Okay, I'm gonna put the 2.01 to the power of 0.3x. Okay, so as you can see, the quadratic, the brown, seems to be a lot faster because the y is a lot bigger, right? But then I don't stop there. I don't rely on my calculator. I tell my calculator what to do. It's a linear algebra. We need to tell the machine what they're supposed to do. They just do it quickly for me. They don't do it for us. Okay. So if I go to Windows setting, yes, I am willing to risk. I'm going to go maybe up to 100. And then see the behavior of the function. So if I make a zoom fit on that, so as you can see, maybe too much. We know that it's going to cut up with the the eventual value. So for the y, let's put 500. Why not? Maybe too small. So let's go zoom fit. And that should be about here. Let's put 1,000. Oops, sorry. -100 to 1,000. Yeah, that's better. Yeah, as you can see, now if I go to 2,000, 1,500. So as you can see, my blue function, the exponential, is going to catch up, right? But you might say, oh, actually, the brown one could be bigger after a few steps forward. So should I increase my domain? It could be your another deduction, but no, right? I wouldn't bother because I got what I needed. I knew my exponential function is going to eventually catch up. So then as soon as it caught up, I stopped analyzing further. So that confidence is required. When you see a smaller scale that you suspect that it's supposed to be bigger, you just have to increase your domain. But the question might not tell you that, so that you need to come up with your own, and that's only possible if you understand the function well. Okay. All right, and yes, another quick tip is that if you got a lot of graph on your calculator, and then you want to delete all that, just press delete 3 times. And if you press delete the 3 times, it asks you whether you want to clear everything. And if you say yes, then you can do it. You don't have to always add the new graph page over and over. And I don't like doing that because some of the functions, some of the parameters saved previously may affect on the result of the graph. So if you want to clear everything, please press delete 3 times. This is my tip. Okay. Oh yeah, I don't think this is very useful. But if I show you how to restrict your domain on the calculator, right? So if I just go to graph again, imagine that I want to have x squared. But as you know, it's not one-to-one function because it doesn't pass the horizontal line test, and we may want to restrict the domain. And how you can do is, remember in the topic 1, we are talking about the given that conditional statement. So here, if I put the bar there, and let's say x is bigger than 0, that is going to only demonstrate the function that is bigger than 0. So if you want to see only a piecewise function in the given interval, you can do that. But I don't think if it's that, I don't know if it's going to be so useful. It hasn't been so useful, but just to letting you know that it's possible to restrict the domain and demonstrate that on your calculator directly. So the typical, I think, example to associate with this is to find an inverse function that is not one-to-one. So for example, imagine that you had a 2x over x squared plus 1, and it looks like that, and maybe I will make it zoom fit, menu 4a, and I got this function, and I would probably find the local maximum or minimum to restrict the domain, right? So if I try to find the analyzer graph maximum from lower bound to upper bound at x equal to 1, it gave me the local maximum. So for that, if I restrict here using the given statement and x bigger than 1, then voila, this function would have the one-to-one function, hence it will have inverse. Okay, is how you can also demonstrate. Okay, but anyhow, yeah, so topic 2 is very popular with the use of a calculator. Make sure you know how to associate with that. All right. And yes, why have I got this trigonometric function? Yeah, function graph. Yes, we can graph it well. But here's the thing. Oh yes, I remember now. Because yes, for trigonometric function, you got to be careful with the unit. You got to be careful with the big difference between the degree and radian, right? And where do you change it? You're absolutely right. On the calculator, my friend. On the calculator, we go to the document setting, right? We go to the document setting to change the unit of the the angle. It can be degree or radian. However, on the hand-shelled calculator, on your physical calculator, if you go to the graph and then change the unit of the angle using the document setting, may not affect on the graph entry. So on the graph, if you want to describe the graph in terms of degree, you shouldn't use the document setting on the graph. You gotta press menu, and then in the menu there's a setting where you can change the unit of the angle there. It's not affected by the document setting angle. So you got to be very careful. So it's very rare, actually. It's very rare. The question asks you to graph the trigonometric function in degree. It has never happened, but in the school test, it often happens. And what students struggle sometimes that it doesn't look like the typical graph that we see, because it has been programmed in Radian. If you want to change into degree, people often use the document setting, but it does not affect on the graph entry angle. If you want to change the angle, please press menu and then change it there, not on the document setting for the graph. But on the iPad version, it's applicable with the document setting, so I cannot demonstrate that. But I want to remind you that it's rare to sketch by the degree, but if you have to, press the menu and change the setting there, is all I gotta say. Okay. Sure, another thing that I wanted to show you here is to use the store function. But before I continue, let me take a 5 and then come back to you. Okay? Alright, let's have a look at the next question. So here we wanted to get the segment, right? So, the reason I brought this one is not to solve it. I did solve it in the revision videos. Please have a look. But, just the use of a calculator, really, right? So I think the formula here was supposed to be, I think the equation was if this is a 2r and this was r, I think it was a 2r squared over 2, and then where was alpha? CAD. Okay, so that's good. So alpha minus sine alpha, and then you had to add by whatever the formula that was, right? But what I'm trying to say here is that I had to use this alpha here, right? But then, you know, to manually put this, right, into the formula, it was just very tedious because you need to press 4 arcsine 1/4 every single time you see the alpha, and we didn't want that, right? So again, what I wanted to demonstrate here is that you are able to use the store function, right, or store command on the calculator. So if I had to deal with the 4 times arcsine, what was it, quarter, right? And I want to use that value over and over. So what I would suggest is that you try to, store it. And I'm going to call it as A. So whatever the value that you put, you press A again, you're going to come back to it. So then you can use it for the NSolve. So for example, you know, imagine that you were solving, let's say, x squared, you know, times A is equal to 5, and you're looking for the x, and you can obviously find the positive length x like that. So what I'm telling you here is when the given constant seems to be very lengthy, no worries. I want you to store the value and then work on it. Okay? So that's that. And then the next thing is, yes, for the inverse norm, right? You know, make sure that if you don't have mu or sigma, that I like to standardize and solve it, but it's a simultaneous equation really, right? So for this one, if you standardize the bounds, it's going to be 2 minus mu over sigma. It's going to be the inverse norm of 0.546. And then 3 minus mu over sigma is going to be the inverse norm of the 0.743 is what I've got. Then yes, you know, for this one, you could have, you know, divided this, but I prefer working with the linear equation. So let's try to rearrange the sigma there. And then, you know, we can just simply subtract the top part with the first ones to just get the sigma notation, right? But for that, you know, I just wanted to remind you, every time you want to do topic 4 statistic distribution, it's all about menu 6, 5. It's always about menu 6, 5. So if you press menu 6, 5, get you to the distribution. You have a normal distribution. You got the binomial distribution. Okay, so inverse norm requires the 2 parameters, mu and sigma. So for the z distribution, so for the area, let's say, so for 0.5 or 4, you know, you're gonna get a negative value like that. So, you know, so please make sure that you're able to come up with the what is the inverse norm using the mu or sigma. If it's not given, standardize it and use it for the z. Okay. And, you know, I'm not going to solve it. I just wanted to demonstrate where you need to access those. So it's all about the topic 4. Please press menu 6, 5. Okay. Sure. And the same thing, you know, I got the, the time taken is normally distributed with the mu and sigma given. That means you can figure out the CDF, no problem. But here's the thing. It's a very, very important concept. I want to remind you this again. So x is normally distributed. That means it's a continuous random variable, and continuous random variable measures by the area. It doesn't matter whether you have the point included or not. It does not matter. So what I'm saying here is probability of x, you know, bigger than or equal to 30 will be the same as probability of x bigger than 30 for the continuous random variable. Okay, but if it's a discrete random variable, it's a little different. Okay, probability of y bigger than or equal to 30 will be the same as probability of y bigger than 29, because it's not finding out the probability by measuring the area. It is finding the area by sum. So it depends whether you are going to include that sequence or not. So you need to be very careful whenever you have the case with the bigger than or bigger than equal to or less than. In that case, you need to check whether you need to subtract by 1 on your bound or not. Okay, you got to be very careful with that. But for the continuous random variable, not so much. So this is going to be same as 1 minus probability of x less than 30 theoretically, but it's going to be the same as the probability of x less than or equal to 30 as well, because it doesn't matter whether you include the point or not for finding out the area. So you can use a calculator for that. And for the calculator, for the CDF, regardless of normal or binomial, it's always programmed for the less than equal to. So make sure you switch around the direction by subtracting from 1. So, okay, so you know what? I got that values. And if you want to use it for the binomial distribution, imagine that I got the probability like that, right? And then you can use your answer, right? So if, for example, if I want to use that probability for the fixed probability of success for the binomial, I go there and I press number of trial. Let's suppose it was a 10. If we want to get the exact value from the previous answer, you can put here the answer there. Oh, maybe not, okay. Or you can store the value and then work on it, okay? That's great. So, you know, not much to discuss as long as you know what it means by PDF or CDF and inverse norm, vice versa. Oh yes, the linear regression. Make sure that you know where to go. So what you need to do is to add a list and spread sheet. And yes, please grow accustomed. Please grow accustomed to name your column. It's very important you name your column. So I'm gonna maybe call it P and Q. And let's put 1, 2, 3, 4, 5, 6. And then let's put here, I don't know, you know, -1, 4, 5, 4, 6, 8, something like that. And if you want to find the regression line, it does not matter whether you want to do the mx plus c or a plus bx. Does not matter. It doesn't matter. So I'm gonna press menu, statistic, and then stat calculation. It doesn't matter whether you want to do the mx plus b or a plus bx. It's gonna give you the same result. Let's check it out actually if it does give you the same result. And here we name our column. It's gonna be P and it's gonna be Q. Voila, that is it, great. So it got me the result of the gradient and then the y-intercept. And then PMCC, Pearson's moment correlation coefficient, is the R. R squared is a coefficient of determination for the AA students. You absolutely don't need to know that, okay? But you know, let's see if you got the same result. If I apply it for the A plus BX, I'm gonna apply the P and I'm gonna apply the Q. But in this time, let's put it in the column E, okay? So as you can see, the gradient is supposed to be the B. Gradient here, as you can see, is the same. You got the same y-intercept, so it does not matter. Obviously, we should prefer mx plus b because we just want to be, you know, working with the point gradient formula where we put the gradient in front. Okay, so that's that. It doesn't really do any difference, so don't worry about that. Okay, but yeah, that's the thing with the regression. Okay. Oh yes, you know, for the continuous random variable, for the topic 4, it involves a lot of integration, doesn't it? One thing that I want to remind you is to find the median, okay? So for example, I wanted to find, let's say that I wanted to integrate the sine x over 4, and I wanted to integrate from 0 to m so that it becomes half. Okay, for that you can use NSolver. So let's have a look. So what you can do is, sure, let's go to the calculator. Imagine that I wanted to find the median. That means you want to find an upper bound in the given interval so that the probability is going to be half. So I'm going to put NSolve. And then let's put an integral. So I'm going to press menu. Sorry, I can just put that. But menu, sure, go to calculus, and numerical integral is what we have there, right? So I'm going to go from, what is it? From 0 to x. I don't know my median. Then the function that I have is, it was a sine x over 4 dx. I'm going to let that to be what? 1 over median's half, and I'm looking for the x, and it's gonna get you that, right? So you can use the NSolver for that. You can use it for finding the first quartile as well. Okay, so it's going to be, let's say, quarter. That's gonna get you. That is great. If you want to find the 3 over 4, it's gonna get you that as well. I press enter, but it's lagging. Long calculation, cancel calculation. Ha ha ha. Okay, yeah, whatever, I'm sure it's gonna work. Okay, so you can actually find the bounds on your calculator. However, you got to be very careful. You got to be very careful here, my friend, especially you're dealing with the periodic function like this, because you can have several solutions, isn't it? You can have a several solution, my friend. So what I'm saying here is, you know, so imagine that you're solving NSolve. Okay, imagine that you want to integrate the sine again. You know, let's say that you want to integrate from 0 to x, that the area, let's say, is going to be 2. Okay, so I want to integrate the sine x, and let's call it x equal to 2. Then, you know, if you put the x, I'm sure it's going to give me pi. So that's great. However, if you remember this, look at this. The sine is a periodic function like this. Okay, and then we just established that up to pi, it's going to give me the area of a 2. I get it. However, it's not wrong. It's not wrong to say, right, that pi, 2 pi, 3 pi, if you integrate from 0 to 3 pi, this area is going to cancel out. You're going to get that 2 over there, right? That's great. So if you wanted to get the 3 pi, what you are supposed to do is to restrict your domain. So, you know, I'm going to say I want to find the 3 pi, and let's say I'll put lower bound to be 2.5 pi. And then upper bound, let's say 3.5 pi. I'm sure that it's going to give me the solution that is bigger than 3.14. It's actually going to give me the 3 pi answer. So if for empiric function like this, you got to be very careful. You need to check your domain and restrict the domain to find the particular solution. So here, if we compare with this 3 pi, I'm sure it's going to be the same value, you see? So yeah, you got to be careful with the solving with the NSolve. But, you know, usually for continuous random variable, it's actually for the very first answer that you're gonna get, so it's reasonable to use NSolve, but just to remind you that you can have multiple solutions. Okay, that's great. Anything else? Sure, we just learned how to find the median and NSolve to find the bounds, so that's great. What else? Nothing much, right? So these are just the formula, so you know, check the revision video. I'm just focusing on what is it, the use of a calculator to compute this. For this one is something with finding the bounds for the integration. So that's great. So that's lovely. Let's move on. All right. Oh yes, you know, this is very important. The reason I got this question is not to follow this question, but just to remind you how we're going to use the graph to analyze the derivative. Okay. So imagine that I was looking for example, if I wanted to find, let's say, the maximum minimum, sure, that you can use your function, no problem, right? So imagine that I want to find that there are functions maximum. You just have to graph it and find the local maximum. So if I go to the graph here, you know, let me quickly just randomly sketch the function. So let's say x cubic minus 2x plus 1. Imagine that I have that function, right? So imagine that I have that function. So for finding the maximum minimum, no problem. I'm going to go to analyze graph, maximum, lower bound, upper bound, and voila, I got the maximum value. That's great. So you can find the local maximum minimum using the calculator. However, if you wanted to find the inflection point, my friend, if you want to find the inflection point using the calculator, here's what I suggest. It's going to be the maximum, minimum of the f prime. So inflection of the fx is the maximum minimum of the extrema of the derivative. So I want you to remember that. So if you got a fancy function, so imagine you got a fancy function like this. Imagine that you have a, you know, let me just draw another like a crazy one I think we saw from the SL exam. So let's say that we have x plus 2 to the power of cosine x, my friend. You know, why not? Why not? And then let's say my domain was defined from 0 to 2 pi. And then suppose that you wanted to find the inflection point, and then we cannot use calculus because we technically we haven't learned how to differentiate that function. It's not polynomial. You have to, you know, put it into logarithmic and etc. But that's not the spirit of the paper 2 question. It's asking to use the calculator to find the inflection point. For that, what I suggest is to use the derivative. I want you to sketch the derivative to find the maximum minimum. And yes, the calculator does not find the expression. It does not find the expression of the derivative, but it tells you the graph of it, right? So what you can do is the following. What you can do is, yes, on the graph, I'm going to sketch, the d over dx of the x, and the x plus 2 times cosine x is what can happen. And then the domain was, again, from 0 to 2 pi. And then if you wanted to find the original function's, the inflection point, where you want to do is to find the maximum minimum of the derivative. So it's a very convenient, isn't it? So then I can go to analyze graph, and then let's go minimum here. And then there you go. And then let's find the maximum there. And that's not the maximum minimum of the f. Remember, these are the inflection point of the, of the original function. If you look at decreasing, increasing behavior of the derivative, that's a concave down to up inflection point for your original function. So please make sure that you're able to graph the derivative as well as the integral. You can actually sketch the integral. That's also great. If you were given the velocity function, if you want to demonstrate the displacement function, you can literally put the integral there, no problem. So if for example, you know that the let's say I'm integrating from 0 to x of the x. You know the integral of x is a 1 over 2x squared plus c. So it's evaluating as a dummy variable and plugging the variable from 0 to x. Then you're gonna get, what is it, x squared over 2, right? So yes, I do expect that it's gonna be a quadratic function. Then voila, I do get a quadratic function. So if you want to sketch the integral and then play around with its value, you can do that. But I want you to be careful, because you got to be careful with the lower bound, because if you integrate, let's say, sine function, you get the negative cosine, but if you integrate from 0 to x, cosine 0 is a 1, you see? So you wouldn't get the exact sine shape, you see? But you can integrate other functions such as exponential. Sorry, maybe I would do the cosine function, why not? So let's integrate the cosine from 0 to x, cosine x. Then yes, I do expect to get the sine x. I have it, right? But for sketching the integral, I think it's very rare, because of the tricky part of the bounds, right? Because it may not be 0 for cosine integral. That's the sine. If you put 0, it becomes a 0, but it's not the same thing for the sine integral. So you got to be extra careful. But for the use of the graph, it's more popular with the derivative. And when you sketch the derivative, there you can figure out many information, such as the maximum minimum at its x-intercept, and checking that the sign changes, or the inflection point of the f, where it's going to be the local maximum minimum of the derivative. So please keep that in mind, okay? Yeah, sure. Gradient of the tangent curve is a 0, so that means you are looking for the, what is it, either the local maximum minimum or a stationary inflection. Or you can simply sketch the derivative of this directly. Why not? Let me try to sketch the derivative of this and just try to find the x-intercept. I think it would be better, because you need to check with your naked eye whether the inflection happens or not. I think it's easy to spot the maximum minimum. Maybe it's not so clear with the stationary inflection. For this one, I'll be relentlessly just graph the derivative right away. Why not? If it was a paper too, obviously, right? So I'll put the derivative. Oh yeah, if you ask me where the derivative symbol is, again, every time you want to get some fancy expression, just press this bookmark here, will you? Here it contains all the derivative, integral, sigma, permutation, all that jazz. So try to access your symbol from that tab, okay? That button. So I'm going to differentiate with respect to x there. Then no problem. Arc sine of x plus 2 times square root over 1 minus x squared is what I've got, right? So I got my derivative there, but I will restrict my domain, my friend. So let's go from 0 to 1. Why not? Sorry, negative 1 to 1. The question asked me to restrict it, so that's what I've done. So if you want to see where the gradient of tangent to the curve is 0, is when the derivative becomes 0. So that's going to be the x-intercept. So I'm going to look at the analyzed graph as 0, lower bound, upper bound, half. It's going to be what it is. You don't have to solve it manually if it allows you to use your calculator. Okay, that is absolutely great. Yeah, that's fine, right? So, and also, yeah, if you want to integrate, yes, sure. If you want to integrate, so it's going to be from, let's say, pi, I don't know, let's just go from 1 to 3. And if you want to get the volume, ln x over x cubic, square dx, sure, you can do that. And for sketching, sure, you can just put a graph on it. But if you want to find the inflection, what do you do? If you want to find the inflection using the calculator, but for this one, exact value wouldn't require the use of a calculator. You have to demonstrate with the use of the work, the manual work. But if I just quickly show you the shape and then trying to see if we can find the inflection point, I would graph, what is it, the derivative. So I'm going to again sketch the derivative of, what is it, it was I believe ln x over x cubic, whatever, let's just go with it, right? And as you can see, it's got a vertical asymptote. So I wouldn't dare putting it to zoom fit, because it's going to give you the divergence in the given domain. I don't want that, right? But if you just zoom in, there as you can see, there's a slight local minimum there, right? So that's great. So for that local minimum is going to get me the, what is it, the inflection point from concave down to up for your original function. So I'm gonna analyze graph, finding the minimum, boom, yeah, that's at 1.79. I know I'm gonna have an inflection point for the f because it's a local maximum minimum of the derivative. Okay. Yeah, you know, the integration, we just talked about how to find the bounds, right? You can use NSolver for the bounds, but you can have a multiple solution for the bounds as well. So you need to double check with your domain, right? And also, if you want to find the area, my friend, if you want to find the area, make sure you put an absolute value, right? So if I have to work with the area of, let's say, sine x from 0 to 2 pi, I wouldn't just put the integral. We go to menu, and where's the calculus and numerical integral, 0 to 2 pi, that is great. However, put an absolute value. Either you can put ABS for an absolute value, it's just quicker for me, or, you know, as I've said before, just press this fancy box here which contains all those fancy operations including the absolute value, and then put your function to find the area. So I'm going to put the absolute value of a sine x, for example, right? X is going to give me 4, right? So make sure if you want to find the area or distance, my friend, you need to make sure you put an absolute value on your function. Okay. Yeah, you know, if you want to find the area between, also you don't have to, you could sketch, of course, but if you find the lower bound to upper bound, you don't have to work with the intersection if it's done by calculator, because you can literally do a to b, absolute value, and then you don't need to see which one is above or below if it was to use your calculator. You just have to find their difference, but make sure you put an absolute value on it. And it becomes very neat because I don't need to find another intersection, because the calculator puts everything positive for you already, so you don't need to distinguish. Okay, so that's the charm of use of a calculator for the integral. So make sure you're able to work with the the calculator well. Yes, you know, you can also differentiate, right? You can differentiate the function. So, for example, you can press menu, and then calculus numerical derivative at a point, it differentiate up to second degree. So first derivative, second derivative, that's also fine. If you want to find the concavity at a certain point, then you can put the value there, my friend, right? Then you can press OK, and then you can put, for example, let's say sine x, and then it's going to differentiate twice and put the x equal to 1 for you, but it does not find the expression. You got to be careful. It only finds the value for you. Okay, so you need to make sure that the that you are able to get only the value, not the expression. For the expression, you have to differentiate by yourself, okay? But, you know, imagine that you wanted to find, let's say, imagine that I want to find the value of x, that I differentiate, that it becomes, for example, 0.8. If you want that, I suggest to use the graph, okay? Because I don't want to use NSolver for this, because if you differentiate, your function is still not one-to-one function. You see, it's still not one-to-one function, so it may have more than one solution in your given domain. So what you want to do is to visualize it by the graph and see how many solutions can exist in a given interval. So do not put this in NSolver, even though it is possible, but it's going to give you only one solution. So unless you're absolutely sure that your function is one-to-one, do not use NSolver. Try to rely a lot on the graphing. So that's why sketching the graph is very, very important. Okay. Yeah, you know, yeah. So all this kinematics is really the similar thing as we mentioned about. It's about the graphing. So actual solving is in the revision video, for the last minute revision video for the AA. I want you to check it out. But here, I just wanted to demonstrate the key sort of commands on your calculator, right? I just wanted to just briefly go over if I missed anything, right? So in this trick, you can find the 3 types of trick: the right angle trigonometry, reciprocal, secant, cosecant, cotangent, right? And then the inverse trick. So that's great. If you press Control, division, it creates the quotient. It's just so more relaxing to use it. If you press this button, it's got all the fancy operation, including the absolute value, derivative, integral, or sigma. Please use it. If you press Control, equal, you can have conditional statement, which you can use it for the evaluation of a certain number of a function, or restricting the domain of the function, right? Yeah, exponent is fine. What else? If you want to, go back, you can press Control Z, just like the redo or undo on your computer, right? And also, imagine that you got many tabs. If you want to move around the tabs, you can press Control left. As you can see, this is going to the previous page. So if you press Control left, it will move on to the page 1.1. And if you press to the right, it's going to go to the page 1.3. That's another thing that I can talk about. And also, yes, you got a lot of graph here. Let's say there are several graph here. You want to get rid of it. Just press delete 3 times, and it's going to get rid of everything for you. Anything else? Oh yes, store. If you had to use that number quite often, make sure you press Control var to access the store. Your answer can be stored into any alphabet. You can override on it. Okay, is what you can do. And also make sure in your column on the spreadsheet, if you want to create the value, make sure you name them. But here's the thing: if you already use the variable for the previous column, and if you're trying to use that alphabet again, it's gonna put it in bold. That means that bold has already stored the numerical value. So if you put P again, it's going to bring up the values that you already have put in the other spreadsheet. So I don't want you to do that. So if the alphabet suggests that it's in the bold, do not use it. Try to find another alphabet that it's not in bold. That means that no value has been assigned. So make sure you don't confuse that, because you can then screw up the data, and that could lead into the mistake, and then it shouldn't happen. Okay, but overall, yes, NSolver, a very, very powerful tool, but do not rely on the use of calculator first. Make sure you understand the mathematics behind it. For function sketching, I need to have a right domain, and am I confident that I'm going to have the solution? Do not rely too much on the NSolver unless it's one-to-one, and also be able to sketch the derivative and integral and use that graph. A sketch graph of the derivative can be well used for finding the local maximum, minimum, or inflection point of the fx. Okay. But yeah, that's pretty much it for me today with the demonstration of the calculator. Good luck for the paper too.